Today we're looking at a common mistake that occurs while computing the area bounded by a velocity time graph, which should give us the displacement of an object moving in one dimension. And the mistake I've seen most commonly when calculating the displacement happens when the student isn't really clear on how the area bounded by a function is defined. So here's an example of a bad solution for our first VT graph. And I saw this, or something similar to this, from about 30% of my students on a recent assignment. And I encourage you to pause the video and just take a minute to see if you can identify the mistake here. So what's the mistake? When we talk about the area bounded by a function, we're talking about the area vertically between the function and the t-axis. But in our shaded area from 6 to 8 seconds here, we're showing the area between the graph of V and the bottom of the grid, instead of the area between V and the t-axis. Well, V is actually negative on this part of the graph, which means the area should be above the graph, like this. Now, area above the t-axis will count as positive, and that makes sense because the positive velocity results in positive displacement. In other words, when the object is moving to the right, it ends up farther along to the right. And of course, any area below the t-axis counts as negative displacement, which also makes sense because the velocity is negative there. Now we can compute the area of each part by using the formula for the area of a triangle on each of these sections. So for the first triangle, we apply the formula 1/2 base times height, and the base has a width of 6 seconds, just keeping the units there, and the height is 4 meters per second. Notice that the seconds cancel and we get meters for our units. So in that calculation, we have 6 times 4, which is 24, and we divide by 2. And this gives us a displacement of positive 12 meters for that time interval. For the second triangle, we apply 1/2 base times height. So we have 1/2 times a width of 2 seconds. And then notice we're keeping the minus sign on the height. So that's how we're going to keep track of that negative contribution to the displacement. So the height of this triangle counts as negative 4 meters per second. Again, the seconds cancel. And we end up with a negative displacement contribution. So that's negative 4 meters. Adding these two displacements together, we arrive at a total displacement of positive 8 meters. Now let's take a look at our second example. In this example, V is always positive, so all our displacement contributions are all going to be positive. But the mistake I saw on about 20% of my papers this time was to shade the graph like this. So what's wrong with this one? In this one, we're kind of shading with respect to a false bottom that matches the minimum value of V. But that's not the area bounded by V. We need to shade all the way down to the t-axis, like this. So now we can get the area by chopping into two trapezoids and using the formula for the area of a trapezoid. So for that, we use the average of the two heights on the left and right of the trapezoid and then multiply it by the width of the base. So for our first trapezoid, we have 1/2 times the sum of the left and right heights. That's 6 meters per second height on the left and 2 meters per second height on the right. That gives us the average of the two heights. And then we multiply by the width of the base, which is 6 seconds here. So in those parentheses, we have an 8. If we multiply that by 6, we get 48. Divide by 2, and we get a displacement contribution of 24 meters. Now for our second trapezoid, we apply the same idea. We take the sum of the two heights and then divide by 2, and then we multiply by the width of the base. So we have 1/2, a height of 2 on the left, 1 on the right, and then the width of the base is 4 seconds. And so we get a 3 in those parentheses. 3 times 4 is 12. We divide by 2, and we arrive at a displacement contribution of 6 meters. Now we can put together our two displacement contributions here, and we arrive at a total displacement of 30 meters. Hopefully this clarifies what we mean by the area bounded by a VT graph, and I'll see you next time.